We are going to start the tournament. Okay, I'm the chairman. Let's introduce each team. Let's first the jury. I'm Tian Yi from the Zhongzheng University. The next one.
林周是从外语的是
张志伟from Indonesia University.
So, good morning everybody. Welcome to Candy and Typt from National Taiwan Normal University.
Hello everyone, good morning. I'm Typt from Hongjiang. Thank you.
Okay. Let's go to introduce the reporter.
Our team name is Scientist, and we come from PF2, and this is Ollie and Jean and Jane and Jennifer and Amar. Thank you.
The opponent.
This is Team University and I'm the leader, Yu Jiao, and this is Chen Ziyu, and Chen Yao,
Okay, for the reviewer.
Honorable judges, worthy opponents, this is the team Wu Yikanhua from Taipei River Senior High School, and I'm the team captain Liu Weifan, and this is Li Qingyu, Yu Yinhui, Xu Kaiyi, Yu Youcai. Thank you.
Okay. I forgot one thing. Have you ever tried to test your video, the projector, your computer with the projector? The recorder, have you ever tried? Connect. Okay, no problem. Test first. Yes, there is. No problem. Go ahead. Okay, no problem. Okay. Check the music. Okay. Okay, let's start again. Please, the opponent challenge the reporter for the problem. 1 minute.
The opponent will challenge the reporter on question number 2.
Question number 2.
We would like to accept the challenge.
Okay. You have to 1 minute to prepare. 5 minutes to prepare.
And please write down your name on the
Oh, okay. Got it. Opponent, fix the floor.
Honorable jurists and fellow competitors, I'm a reporter from King Science, Junior High School. Today I'm going to present our two oscillating sphere. And the purpose statement is a light sphere with a conducting surface is suspending from a thin line. And when the sphere is rotating about its vertical axis and then released, it starts to oscillate. Investigate how the presence of the magnetic field affects its motion. And the main focus is how different parameters affect this sphere oscillate. This is the process we're going to present today. Let's begin with observation, that's the theory, and experimentation, that is the conclusion part. And this is the observation video. As you can see, a light sphere was suspending with a thin wire, and when we give it the initial rotation angle, it starts to oscillate. But when we give it the magnetic field, the amplitude will decay. And we can see from this graph, the break is we don't provide the magnetic field, and the amplitude will decay. And the red is because about the air resistance and the torsion damping. And the red one is we provide magnetic field. We can see the amplitude will have more decay, and that's because the magnetic damping and the air resistance torsion damping. And let's come to the theory part. About the sphere, we can imagine there are so many coils in the sphere. And when the magnetic direction go to this way, and the sphere starts to rotate, and then based on the net flow, there are variations of the magnetic flux. It will generate the induction current. And this picture is about the charge density and the current density. We can see at this point, when the current is go to upward and the magnetic field is go to the forward, then it will generate the magnetic force, then opposite to the sphere's rotation directions. And this we call the magnetic damping. And this is about the charge density. We assume the sphere thickness h is smaller than the sphere radius a, and only one layer electronic on the surface. And this is some equation about the current density and the continuum equation. And because we consider only one layer electronic, so the charge distribution is constant. And then we calculate with the coordinate systems. We can see the magnetic force and the charge density equation. And the low T is about the tangential charge density. And here we list the net force and the net torque equation. And we can see the net force is equal to 0. But the net torque is not equal to 0. That's because if the force is 0, that means the sphere will don't move. But the torque is not equal to 0. That means the sphere will rotate by the vertical axis. And then we list the net torque by two ways. The first one is about the current density. We can express by this equation. And the net torque is by the moment of inertia of the hollow sphere. And then we combine the net torque equation like this, and we can find out that the angular velocity has the exponential damping. And this equation indicates that the spinning sphere decelerated exponentially. And we define this fraction is called alpha. And then it's about the decay time. We consider the air resistance and the wire torsion. And the kappa is the torsion constant. And alpha means the magnetic damping. That's called the magnetic decay time 2. And the gamma called the frictional damping and the friction damping decay time. And the delta calls the total decay time. And because the amplitude decays exponentially, so we can write our equation like this. And here's come to the experimentation. And here we use two types of magnetic wire. One wire diameter is 0.5 millimeter. That to make a PF2 coil. And the other one magnetic wire, the diameter is 0.1 millimeter to suspend the stainless hollow sphere. And we use the power supply to change our magnetic field and use the Gauss meter to measure it. And here is the setup. First, we power up the PF2 coil to generate the magnetic field and then adjust the sphere to the initial rotation angle. It starts to oscillate. and we record the video until 600 seconds and use shaker to analyze the amplitude. And here is the graph about before we talk about the background experiment, let's talk about how to analyze the amplitude. And this is a graph about we provide 12 gauss and the initial rotation angle is 25 degrees. And we record a video from 0 to 1100 seconds. And we can zoom into this 0 to 200 seconds. You can see the amplitude will decay. And we find a peak and do some exponential analysis. We call this number delta, total decay time. And here, in the about the theoretical value, we can find the magnetic decay time alpha by this equation. But how about to find out the experimental value? So we will measure the total decay time delta in the non-magnetic field situation. Because non-magnetic field, so the delta don't have the alpha. We only calculate. We just need to calculate the fusion decay time gamma. And here we do some experiment about the non-magnetic field. And then the delta is like this. And to put it into this equation, we can get a fusion decay time gamma. And this gamma equals to 170. We use this number to do our experiment 1. And here is about the experiment 1. We change the magnetic field and control the initial rotation angle and conductivity of the stainless sphere and the mass and the radius of the stainless sphere. And the dependent variables is about the delta total decay time. And here we use the 12 gauss and 10 gauss, 8 gauss and 6 gauss, 4 gauss and 2 gauss to calculate and do some exponential analysis to get this number, delta, total decay time. And here is the strip about the magnetic field and alpha and the delta gamma. And we can see the alpha TH means that the magnetic decay time, theoretical value, and the alpha ES means the magnetic decay time experimental value. And let's come to the discussion part. This graph is about the magnetic field to the alpha magnetic decay time. We can see when the magnetic field becomes bigger, then our experimental error will decrease. That's because when the magnetic field is big enough, magnetic damping could be the main damping in these systems. And when the magnetic field is small, like this one, and other friction damping influence could become bigger in this system. So we do rewrite our equation like this. Maybe we can change the gamma is frictional damping term to gamma 1 like to express the air resistance, or gamma 2 to express the value resistance. And then in the experiment 2, which we change the initial rotation angle. And here is our initial rotation angle is about 120 degree, 90 degree, and 60 degree, 30 degree. And then we combine each other. We can see when the rotation angle becomes bigger, then the friction damping term will increase, and the variation of amplitude decay will also increase. And here comes to our conclusion. About problem statement, it said how to investigate the presence of the magnetic field affect the motion. And our main focus is how different parameters affect. And the parameters is the magnetic and the frictional damping. So about the conclusion, first we want to know why the magnetic cause the damping. Yes, because when the rotation axis is vertical with the magnetic field direction, the magnetic field will generate a resistance opposite to the field direction of the rotation, and the amplitude will decay. And this decay is exponentially. And the second one is about the amplitude decay. And we can find out from this equation, magnetic field square is inversely proportional to the magnetic decay time. And that one is about the initial rotation angle. When the initial rotation angle is increased, then the friction damping will become bigger. And then there are some more variation about amplitude decay. And this is my report. Thank you for listening.
Now the opponent question, ask the question to
in the breakdown to check. This breakdown.
How do you fit on the speed? Fit on the speed.
Fit on speed. We use the test on test.
Next question is, how do you fix your vertical axis because there might be something there. How do you fix your vertical axis?
Vertical axis means the vertical
Axis.
vertical axis. That could be the experimental error because we use the magnetic wire. It could be some. It will not be line. It could have some terms in it.
Okay. Well, next question, you start with the 90. In this function, there not mention the type of the friction, but all of the base edges you mentioned that there are many types of the friction. Why didn't you talk about the friction?
Time's up. Sorry. Opponent prepare your report. Opponent takes the floor.
Okay. I'm the opponent from Team Chocolate and well, first, I want to talk about the proper statement. The light sphere with a conducting surface is suspended from a fixed wire. When the sphere is rotated about its vertical axis, thereby twisting the wire, and then released, it starts to oscillate. Investigate how the presence of a magnetic field affects the motion. And here is my summary of the reporter for his pros and cons. And for the first observation video, I think he is good at showing the phenomenon. And but I think the cons of it is that he didn't have enough explanation of his observation video. So next is the parameters discussion, and he talks about the magnetic field strength and other parameters. I think he has a great, clear explanation. And here is about theory. He talks about the eddy current, charge density, net torque, decay time, and I think his pros of the theory is that he has explanation and great formulas, and the cons of it is that he didn't have a full explanation about the equations associated with the parameters. And next is the pros and cons of the experiment. And I think his pros of the experiment is that he has a quantitative comparison, and he has a great square value. And the cons of it is that he missed the parameters talked about in the theory. And the conclusion is that he has a great quantitative comparison between the theory and the experiment. And the cons of the conclusion is that he lacks of the qualitative analysis and the main parameters. So here is my opponent question. And for the first is first question to the reporter. Can you explain me about the friction you didn't mention in your theory, just like in the calculate?
In the theory about friction force.
Yeah.
We can measure, we can calculate because we need to consider the air resistance and the torsion damping. So by ourselves, we cannot calculate. So maybe in the future we can.
How about if you think about measuring the frictions in the experiment, just like the air resistance, and change some parameters to measure the friction? Have you ever tried to make it?
In our experiment, we use the non-magnetic field. So that means they don't have alpha. So if we get this number,
but there you show the many types of the friction in it, but I think you may have to separate every single parameters in every single experiment, because the parameters only have one type, just like you just talk about the friction, but not any type of friction to make a parameter.
so we'll do it in our future and divide the gamma into the side, like you say, the air resistance. Air resistance is one term and the torsion is the other.
The next one is how did you calculate your magnetic flux changes?
Pardon?
Here, how did you calculate your magnetic flux changes?
We apply the charge density. Because this is the charge density picture, and by some current density, so we can calculate the magnetic flux change by some by the mass law and the lowest force.
Can you turn to page 9? The air resistance. Where can I find the air resistance in this page?
This page only consider the magnetic term and the torsion that the magnetic damping cost. Now we give it the initial rotation interval. The rotation is by the magnetic term.
And how about the tension of the sphere of the rope up, just right off the sphere? Have you ever considered about it? The tension of the rope, twisting force.
Just give it the initial rotation interval. Don't have the interval velocity to push.
didn't, you haven't considered about, you can talk about it again.
We don't give it the initial rotation, initial angular velocity, only give it the initial rotation angle, and then release. And because the torsion, so the sphere will start to oscillate.
Okay. How about you say your current on the sphere surface is that eddy current, and how can you relate it from the theory and the experiment?
And just like this is the stainless out of the field, and the red one is the coil. And what we can see by the current, eddy current. So because eddy current is some many circles about the current, right? So we can imagine there are so many coils in this field, just like many current.
Yes.
And then because there are some regulations about the magnetic flux. So because magnetic flux change, so it will generate an induction current.
Okay, and what do you think about the different strength of the eddy current on your surface? Just like the eddy current is average or somewhere is everywhere.
Because this is a conducting field, so it will happen everywhere in this field.
And the sphere might not be very
Not uniform. Could this have more current density? And like this one, the current density is less, more less.
And for the next question is, how about, do you think the friction is static or kinetic? The friction of the rope is static or kinetic?
The friction, the total torsion friction will not be the static because we give it a different initial rotation angle. So because the different rotation angles, they will give it a different torsion density.
This is in the theoretical explanation. Can you show me about how do you explain it in your experiment results? And can you observe it from your experiment? So
You say the friction term, or
just like in your graph, can you see whether it is the static or kinetic in your graph?
we didn't. If we want to find out the difference about the friction, that means our experiment 2, because we changed the rotation angle. So about the experiment 1, we didn't change, so the gamma will be also static. But experiment 2 will not be the static, but we didn't find out yet. So that in our future we can to calculate about the delta and gamma to write that equation.
And have you considered about the texture of the ball or the rope? Will it affect the result? The texture of the ball or the sphere, will it?
The texture of the sphere is about because we have this one coefficient called conductivity of the sphere, and this conductivity will be based on the sphere's text. So when we use the aluminum or we use the stainless steel, the conductivity of the sphere will change.
The next question is, how about the distribution of the eddy current?
And this is the distribution about any curve. You can see this.
So this is matches your experiment. It is for this theoretical graph matches your experiment. And how about you set a place on the sphere, and do you think it will affect the rotation inertia of your sphere?
because when we put the plate on the sphere, it will average. It is the average term. So it will don't affect this motion.
But will it affect the period or? So you mean the place on your sphere will not affect the angular velocity or the but the in rotation inertia equals m/r squared. But I think the plate will have the mass to affect the sphere rotation.
It will affect the moment of inertia.
Because
we put on the plate, so our moment of inertia may change. Not only consider our sphere, we need to consider the plate on it. We miss this one, this one.
so you mean the mass of the plate didn't affect the.
It will not affect about the eddy current, but it will affect the torque about the sphere.
Yeah, so you mean the torque of the plate will affect your rotation? And have you considered it about like you set up?
Because in our plate is used as circuitry, it's very light, so we didn't consider it.
But I think it might not be very light. So our next question is, okay, I have no other way to say it.
Perfect. Open and summarize the discussion.
So here is my conclusion about our discussion. So I think the recorder has great theory and experiments, and he can actually match it in a way. So the results feel pretty qualitatively, but I think he didn't explain every theory equation very well, and I think he missed important parameters for instance, air heat resistance, wire tension, and I think he is said about the important quantitative analysis.
Okay. Okay. Prepare check the floor to question the reporter and the opponent.
So first, we appreciate the reporters and the opponent's effort on this debate. So now, questions for both. What parameters do you think that influence the whole phenomenon the most? So first, reporter.
The proposal is, I think, parameters is the magnetic term and the damping term, and friction parameter, magnetic and friction.
So you're focusing on the damping part.
Yes.
Okay. And what about the opponent?
I think so too, but I think there is still another friction. So.
Okay, so as both reporters and the opponent have mentioned the friction and the torsion damping, I would like to ask if it's not placed in a magnetic field, and how would these two resistance influence the damping motion? So first reporter.
You mean there are two damping motions about the resistance and the torsion.
Yes.
And maybe it have some other friction force on it, so but we didn't find it. Our future was to find other friction.
I mean, how would it how would the amplitude decrease? Like fits the line.
The air resistance is because the resistance is equal to
It's proportional to like square
the
velocity.
velocity squared.
Yes.
So, but like the torsion damping is a linear.
Linear. Okay. What about the opponent?
And I think the friction will be opposite to the motion direction. So I think it will make the amplitude decreases.
Okay. So I've got a question for reporter. Can you turn to the PowerPoint slide on the equation part? May I ask what does the upside down triangle means?
then this equals to 0, and we can calculate the E and the E equals to magnetic field.
And so next page, how do you define the whole coordinates in your theory?
Then hold.
I mean, like the phi and the theta, like how do you define it?
Yes, theta like a, and look at this point, and this point is to the center, and the center to the SY center. And this theta means this point to the SY, and the phi is about the
Time's up.
point to the
2 minutes for the reviewer to prepare. Okay, the reviewer takes the floor.
So, again, appreciate for the effort from the reporter and the opponent. I'm Shikai from Team Uli, representing Typt High School. So now I'm starting my review. So first, here's the problem statement, and the focus from the reporter is on the examination of different parameters. So first, the reporter's phenomenon is focusing on the amplitude decay, and the theory is first the magnetic damping caused by eddy current and torsion damping, net torque exerted by torsion, discussion on the kappa. And the air resistance, it's a pity that the reporter didn't focus on it that much. And for the experiment, the magnetic field twins and the initial rotation angle is considered. So first, talking about the pros of the reporter. First, clear and detailed explanation of theory. This is well presented in the report, and many graphs demonstrating the motion makes me very clearly understand what the model is, and the quantitative results. And for the cons, it's unfortunately they didn't elaborate on the damping caused by air resistance, although he did mention it. And certain text should be enlarged since like the coordinate part I didn't get on that much, so to speak. And for the opponent, the pros are pointing out the defects in the reporter's formula, like different types of friction. And they mentioned more parameters like the textures of the sphere. For the cons, ambiguous in analyzing the performance of the reporter, like using words great is a little bit unclear and should include more own opinion during the discussion. So for the first discussion, the opponent asked if friction doesn't really mention in the theory, and the reporter said they could not calculate it, and for the reviewer, we believe that it should be considered and deducible. For the next discussion, the opponent asked parameters should be separately discussed, and the reporter accepted it, and also the reviewer agreed. For the third discussion, the opponent asked if the reporter calculate the magnetic flux change, and the reporter said it is calculated through the charge density, and we agree with it. For the next discussion, for the tension of the string considered, and the reporter answered they only considered initial angle, but for the reviewer, it doesn't really matter in the whole phenomenon, since the tension of the string only works on the vertically axis, which doesn't really matter, which doesn't exert any torque on the whole phenomenon. So the fifth discussion, the opponent asked if value of eddy current strengthened, and the reporter replied that eddy current strengthened everywhere on the sphere, and we will also agree with it. For the sixth discussion, the opponent asked if the friction is kinetic or static. The reporter answered for a different angle and different torsion damping, but the reviewer thinks that this question is a little bit ambiguous, since the friction in the whole phenomenon should be by what they both mentioned, which is first, the air resistance, and second, torsion. But these two forces doesn't seem to be considered in kinetic or static ways, so maybe the opponent could be elaborating more on the question. And my review would be here. Thank you.
Okay. The conclusion from the reporter.
And the first one is about our experimental parameters. And we consider the magnetic field and the initial rotation angle in some damping terms. And the second one, we compare the theoretical and the experimental value in the relationship between the magnetic field and the magnetic decay time in our experiment 1. And third is about the opponent's device. To separate the parameters of our experiments and consider more parameters like the initial angular velocity and about theoretical. The first one is we consider the eddy current that's flow in the right-hand row could cause magnetic damping. And second one is about we list some equations about the magnetic and the friction damping. And the third one is about opponent's advice. We can rewrite our equation in the future mode that describes the friction damping in the moment of inertia. Thank you.
Okay. Comment from the jury.
I have a question from the reporter. Do you think the magnetic damping will either increase or decrease the period of your oscillator?
You mean the force by the magnetic force or the torque?
The magnetic damping caused by eddy current.
Because we
Do you think the period will increase or decrease?
will be always the same. Period will always be the same.
Can you show me your result from your data? Don't you think the period will increase?
I don't think it will be increased because you can see from this graph the peak from the 0 to 200 seconds will be the same numbers. Like this one has the 1, 2, 3, 4, 5, like the 15 peaks, and also you add the magnetic field, you have the same peaks.
Thank you.
Is there AC magnetic field in your laboratory?
We use DC, but I think if we use AC, that will change the magnetic field direction. And we consider the directions to these directions, right? And this direction will cause the fields to magnetic damping. When the magnetic field goes to this way, and this will cause some force to push the field. And one direction is to push, and the other direction is to make a decay. So the magnetic term could be it will cancel each other. and it will affect this motion. Will not affect this motion.
So if you set up, what is the effective thickness of the conducting surface? Yeah, because in the question there is
The
the
thickness
slightest
is
deal,
1 millimeter.
1 millimeter. Yeah, so it's a hollow steel.
Yes.
Oh, I have another question. Let's go to the picture you have showed the oscillation. This one. It seems to me the dark period and the red period, there's a mismatch. Right?
Maybe some, because our,
The red one period is a little bit smaller, right? Can you check the period? One thing is that. The other is that I have to ask the question, the damping made by, caused by the magnetic field, was that proportional to the velocity or velocity squared? Because for
It will
the
not
theory,
proportional.
let's go to the theory. There's a damping term, yes, the net force F equal to that one, and tau, it should be proportional to V, right? You have to try to check the damping constant then. Since you have that damping motion, right? Equation for the damping motion. The previous one.
this is the magnetic damping.
And then the total equation of the equation of motion. Do you have that one? Now you have
Total
alpha.
decay over the friction force.
Yes.
Total decay. The total decay is about.
Yeah, this one. This one. You have alpha, 1 over alpha plus 1 over gamma, right? That's omega dot, right? Omega dot means velocity, right? So it's proportional to V. But let's go to the problem. You have to,
Omega dot is angular acceleration.
yes, it's velocity, right? Okay, no problem. Let's go to the next one. You have the initial different angle that occurs the different decay rate, right? You put the sphere, rotate, then release it. Release some angle, then release it. You release from the different angle that give you the different decay rate, right?
Yes. So we didn't use we didn't to calculate the different terms of.
No, well, I don't care. Let's go to the result. You have the different angle to give the different decay rate, right?
We didn't get the number like data. We only get the delta in the.
No problem. No
experiment
problem
one.
with that. Can you explain why alpha depends on the angle? Sorry, I'm asking a question because I see you can do better. The last question would be, since your equation gives the alpha proportional to b squared, 1 over b squared, right? Okay. You have drawn the diagram of the alpha versus magnetic field. You have drawn the diagram?
Yes.
Alpha versus the magnetic field, right?
This one.
This one. This is just a suggestion. Please draw the diagram. Alpha versus 1 over b squared. You will get a linear. That would be good demonstration. Okay? Okay. You see my problem? Let's jury. No problem. Any problem? Jury. What are you holding? 8778. For the opponent, 67876. For the reviewer, wow, look at the people. 78986. We have all the numbers. Okay. That's the end of this one. Okay, let's have the 10 minutes break. Wonderful program.
Honorable judges, worthy opponents, this is Team Uli Tanhua, and our team would like to challenge problem number 8, Euler's pendulum.
We would like to reject.
Okay.
Other than problem number 8, we would like to challenge problem 15, pancake rotation.
No, no.
So we would like to challenge problem number 2, oscillating screw.
Oh,
Not two.
not
Then problem number 9.
no.
It's problem number 9, oscillating screw.
We all accept it.
What about your name? You presented. Your name will be presented.
Team Togo Team presenting to you
Oscillating screw. So this is our table of contents. We'll start with the problem, and then we'll move on with some observation, and then we'll discuss the parameters, and then the theory, and then the experiments, and we'll end in conclusions. So first is the problem. When placed on its side on a ramp and released, a screw may experience growing oscillations as it travels down the ramp. We think that growing oscillations is important. So investigate how the motion of the screw, as well as the growth of these oscillations, depends on the relative parameters. So we observed, and the results of observation is that the incline angle and the shape of the screw affect the motion greatly, causing different amplitudes and periods, and as well as flipping down the slope if screw is too short. And so the parameters that we discussed are, first, the motion would certainly depend on inclination angle of the slope. So that is how steep the slope of the ramp is, and also the screw shape, which is the length or the radius of the screw, and also the mass of the screw, and the texture of the plane, which changes the friction coefficient. So when talking about angles, we can put them as three different kinds. It's small angles. So the screw rolls and rotates about a pivot point and pendulates until stopped by friction. And for moderate angles, the screw will perform more roll and rotating. And increased angle will cause an increased tangential gravitational acceleration. So it might overcome the friction force and start a sliding motion. And for large angles, the screw might not come to a stop and just slide all the way down. So let's start with the theory. So first is the structure of the screw. So the screw is a rod structure with uneven mass at both ends. So it has a head. This is our head, and this is the tail. So we can assume this big head as the bottom of a cone. So the radius is the same here, and the height of this cone is the length of the screw. So now we, in our theoretical and experimental model, we assume that this is a cone. So, so note also that the screw lies on its side with an angle between ground and the axis. The omega axis on the radius. So now when we place a cone on an XY plane and it starts rolling, it has contact with the XY plane along OA. And OA is an instantaneous axis of rotation here. So now the cone is rotating this way around the Z-axis, and also for OA. And then we have the rotational inertia of the cone and the kinetic energy of the cone. And then we place the rolling cone on the inclined plane. So now we assume that the screw is fixed on the plane and rotating about a pivot point. Then the rotational inertia would be the same because we only change the coordinates into a slanted ramp. And now when oscillating, it can be viewed as an SHM system. So it can result as x double dot will be, this is the gravitational force, and also with the friction force as a vector since it changes. Phi is the incline angle. And so now if the cone rotates at an angle of psi, then we have I alpha being tau, and so we have these equations here, and substituting I into the equation, we will get to this equation. And so for the period, this will be 2 pi square root of this flip. So yes. And so we can conclude and make prediction that the screw on the plane depends on friction. So we can see that friction here will affect the motion. And the oscillation period is dependent on the inclined angle, phi. So in the last page of the period, that we can see that phi also affects the period. And also the period of the oscillation is dependent on the shape of the screw H and R. H and R will change the rotational inertia. And the oscillation growth can be seen from the growth of K. So we can see that the amplitude will grow. And the screw may experience a torque that is able to make it flip downhill. So now is the experiment part. So the first is how the angle of inclination affect the oscillation of the screw. So we classify it as small angles as we put as 30 degrees, moderate for 45, and large for 60. So first we place a 1 centimeter screw on a 30-degree inclined plane with P240 sandpaper. And now we record rolling motion using slow motion. And we analyze the motion using tracker software. And repeat the experiment on 45 and 60 degree inclined planes. So now, so we can see that when the screw is placed on a ramp and rolling downhill, it will experience oscillating. Now when we change the angle to become a so we have the results of first for 30 degrees, the 1 centimeter screw experiences oscillation with minor sliding. It ends in a stop. So from the graph here, we can see that it actually has decreasing oscillations due to because the gravitational force, tangential force is too small and plus friction, so it actually experiences decreasing oscillations throughout the motion. So this is the graph of theta R2. And for 45 degrees, the 1 cm screw experiences growing oscillation while sliding down slightly. And so oscillations here increases, and it actually does just kept sliding down. And then for 60 degrees, the 1 centimeter screw experiences growing oscillations, but because the inclination angle is so big that it just slides down the ramp. So you can see that sliding is very dominant here. Well, you can see a little bit of oscillation. Okay, so it's the second experiment. So now the goal is how the shape of the screw affects the motion of the screw sliding down. So we have half centimeter, 5/8, 3/4, 1 and 1.5 centimeter of screw. So now first we place the half centimeter screw on the 45 degree inclined plane. And then also the same, we record the rolling motion and analyze the motion using trackers. And we repeat with all these different screws. So we can observe like this is the longer screw. And in the results we can see that so for a half centimeter screw it slides down very quickly. And for the 5/8 one, we can see that it also slides down a lot, but because it became longer, so it's at the end when friction force has affected the motion more, it starts to show its oscillation. And for 3/4, we can also see oscillations here with a lot of sliding. You can see that this is the proof that it flips during the motion. And for 1 centimeter, it would be the same as before. It would have increasing oscillations. And for 1.5, we can see that because it's became very long, so its oscillation is very obvious with minor decrease. And so we can put this in a graph resulting in 3 different kinds of main different motions. So one is that slipping is dominant, which means that the screw just slides down the plane very quickly. And the second is the oscillation increases while slipping down the plane. And 3 would be oscillation decrease. And for the third experiment is how the coefficient of friction affects the oscillation of the screw. So we have 3 different sandpapers, which is 100, 240, and 800. And 100 being the largest in friction coefficient. Well, this is the least. So we do the same thing and we place 1 centimeter screw on 45 inclined plane. And now with 3 different sandpapers, and also we analyze the motion using trackers. And so now for results for P100, you can see that friction force is very strong, which affects the which has mainly oscillation motion with a slight decrease. And for P240, it's the same as before with the 1 centimeter screw, so it has experiences increasing oscillation. And for P800, you can see that friction force is very small, so you can see minor oscillations, but slipping would be very dominant. So we also put this into a graph as the results, and we can see the results here. And so we can confirm that by changing the incline angle, it is very obvious that it plays a big part in affecting oscillation. So for small angles, the oscillating is very dominant, and there is little sliding movement, while for large angles, sliding is very dominant. And confirmation 2 is that the shape of the screw. So we changed the height in this experiment, changes the motion drastically. So a shorter screw had a shorter period. And confirmation 3 is that the friction coefficient of a slope changes the motion of the screw also. The smaller coefficient, meaning the friction force is smaller, the easier the screw performs flipping and slipping. And now the slipping motion is more dominant here. And for larger coefficients, the more fixed oscillation it does. So we can conclude that larger incline angles is shorter periods, longer screws is longer periods. And sometimes short screws and large angles will result in flips, flipping down the ramp. And also small friction coefficients would mean a sliding motion. And the big
Okay, question for the opponent.
Okay, appreciate for from the reporter. So first I got some questions. So first of all, can we go back to the observation pages? Like this is the right. The first the observation. Like when you're at yes, you're simulating the space. Okay. Have you ever observe how the screw is placed on a table? Is the contact point really refers to the hat and the end of the shaft?
I believe that when the screw is placed on the table, it touches the table with these two ends. And when we approximate it to a cone, we can barely see that the infinite contacting
Just to clarify, I mean, if you place it on a plane, should it be like this point and this point instead of the edge here? Have you ever considered this or
no, I don't believe that's useful.
Okay, so we'll talk about it in later discussion, and I would like to ask why would you express it as a SHA motion in backwards? Since for SHA motion, you should write the equation into like F equals KX. There should be a substituted K, and I didn't see it in your presentation.
For the SHM, we can see it's on the ramp, it's a projection.
Is it projection?
You can't show it in SHM.
Okay, and that
This
would
is
be
the force.
a pity that you didn't like compare your theory with your experiment. And I guess the question will be here, and we'll continue in the discussion. Thank you.
3 minutes for the opponent to prepare.
honorable judges and reporters. So, 我是徐凯义 from 景武汉话 representing Typt Legal School and Page. So here's the problem statement, and I believe the reporter's team's focus, although not clearly mentioned in the report, is the parameters which impact the whole motion, such as the inclined angle, the length of the screw, and etc. So for the phenomenon, the reporter team emphasizes the rolling motion in the introduction of problem. And the theory, they use the structure of the screw, which they approximate into a cone. And the XY plane rolling cone motion, and of course the SHM model. And for the experiment, they have tested inclined angle, the shape of the screw, and the coefficient of friction. So the opponents believes for the pros of the reporter, so first, they have experiments to test different parameters, which is, of course, and quantitative results, clear numbers, and graphs explained one by one, and I appreciate that. But for the cons, they've lacking quantitative comparison between experiment and theory, just like what I just asked in the question part, that they didn't compare the SHM model that they provided with the experiment results. And for next one, they use time more efficiently since the steps of the experiment were repeated several times when talking about different parameters. And also, the page number is hard for us to refer to like the pages. So now I would like to invite the reporter for further discussion. So first of all, I would like you to elaborate on the SHM system since I want to continue the discussion.
When the screw is placed on the ground, then we can have a projection.
Oh, so that is just a very preliminary prediction, right?
Yeah.
So I would like to ask if you ever analyze the forces on the whole motion, since you mentioned there are gravitational force and friction that is working on the whole motion. Have you ever work on it, the force analysis?
This is our course of thinking.
I mean, Jerry, can you use the backboard?
Yes.
Use the backboard.
Yes, go ahead.
So first, let's just now we're just focusing on the ramp, which I'm looking straight on the ramp. So I'll define this as x-axis and this for y-axis. So if you place your screw like this, and just like what your the simulation that you ignored the fact that is actually not the point pointing on the floor. I'll just use this graph. Could you analyze, draw out where the gravitational force and where the friction are in your theory?
So gravitational forces.
This is the ramp, so you can just draw probably straight down, right?
Yeah,
Okay.
and the friction force.
The friction.
Do we have sliding here?
Do we have sliding here or not? That would be a problem that I would like to discuss. So, since you have discussed the XY plane motion, that it seems that you're regarding the rotating motion as a pure rolling, is it?
Yes, for the X.
But you do know that for the gravitational, I can separate the whole motion as two different kinds of, first, for the pure rolling, like what the reporter just mentioned, which is a cone rolling on the XY plane. However, the sliding motion is really like what the reporter has mentioned. It dominates the whole motion most. So I believe there are two kinds of
motions that the screw are experiencing in the whole motion, which is first the rolling part, and second the sliding part.
Yes.
Yes. So, what was your question about, like?
No, I mean, if the screw is only rotating here, there's one.
But there should be gravitational force, right?
Yes,
Although
there
it's
is.
only swinging in, like, not sliding, but there should be gravitational force,
Yes.
right? So what about friction? How does the friction, like, balance with the gravitational force?
The screw is intended to slide it down
Yes.
because of gravitational force.
Yes.
So we have a friction force pointing. The precise vector I can't predict, but it is pointing away from the gravitational.
Pointing away from the gravity. So let's say that you've got two contact points on the ramp. So I'll find it here and here. So which means the frictions would be working on these two contact points, is right?
Yes.
Okay, so can you please draw up like where the directions of the frictions are?
We can put it as if it's sliding down, it's this way, and
Yes.
if it's rolling, it would be, I guess this way.
So which direction is it actually, or is the friction the sum of these two, like, forces?
For these two, it would be these. This.
Yes.
These, yes.
And what about for the rolling motion?
And for me, I don't think that we can put the sliding friction and the rolling friction as one.
Well, that is what the problem is interesting. Since if I separate the whole motion as first the pure rolling, which should be considering static friction, but while when I'm considering the sliding motion, it should be a kinetic friction, right? So that leads to a question that, because it is impossible for the whole motion to, like, emerges two friction. Like, it couldn't have both friction, which is kinetic and static, right?
I don't mean that it has both kinetic and static.
So how would you explain these two directions of friction?
I would explain it as if it's not sliding down here, then this would be a static friction.
If it's not sliding down, what about if it's sliding down? Because
Then it would be kinetic.
okay, so then if it's sliding down, like we're talking about the
You mean so like if it's comes here.
I thought the whole motion would be like the screw starts from here and they swings back,
Yeah, I mean like if it swings and it
Swings.
stops here, yes.
stops here.
And it just keeps rolling from here.
Okay.
Yes.
But I'm just talking about like the initial
You mean the initial condition of
Yes.
the screw?
and the force analysis, which I want to focus on.
Yes, so this is the force analysis. You mean that's this screw here
Yes.
is about to slide down.
Yes. And how would the forces, like, what I want to focus on is how does the friction causes the swing for the whole motion. Because swing back and forth means that the frictions changes through the whole motion. So for me, I would like to separate the whole motion into four phases. For a screw starting from here, which starts sliding here, and I'll define this as like the middle. So when it swings here, should it be accelerating
Yes.
or rolling?
Yes.
And so it slides down and swings back here.
Yes.
When it swing up here, is it decelerating or accelerating?
Decelerate.
Okay, so I guess we could analyze the whole motion as this is the first phase.
Yes.
Swing toward the middle,
Mm-hmm.
and after this, swing back here, and again, back and back.
Yes.
Yes. So how do you think the friction, like the direction of the friction would change in these four phases?
For me, I would I would still put sliding.
Yes.
So we can see that this rolling back from here to here,
Yes.
and it also slides down from here to here.
Yes. So how would the friction?
Then we can have this friction as pointing this way, and
Okay.
the sliding friction would change. The vector would change throughout time.
And what about the value of these two directions? Since I guess you meant that if it's sliding down, that means the friction is
It's
kinetic,
kinetic.
which means it should be a constant, right?
Yes.
The value should be a constant. Therefore, if I separate this constant friction here, since you have separated into first, balancing the gravitational force, second, providing the accelerate or decelerate for the moment motion.
Yes.
So which means this value changes through the whole motion. Since, or do you regard like the
I regard this.
as a constant too?
No, I regard the screw rolls like this, and this force direction changes. Like if it starts to roll here, this friction will point here, but if it keeps rolls here,
Yes.
it
So
will point here.
as the direction changes, since you're separating the force into two components, would the value of these two components changes in the whole motion?
This friction force would change while this force,
Oh.
because the acceleration of the screw changes.
So you mean that this force is always exists, and while this force's angle changes, right?
And
Since you got
yes.
like different weights.
yes,
But the sum of these two vectors are remaining the same value. Is this what you mean?
remaining the same value.
Like, since
You
you
mean the
mentioned
the vector sum?
yes, since you mentioned the kinetic friction should be constant.
Yes.
Okay. Maybe jump to the next page. Okay. So I guess the force analysis will be here. Will be up here. Next page. Yes. So now I'll just go to the experimental part. Can you change the recorder? Can you move on to the demonstrating page? Have you ever considered the gaps, like on the red? Since if you put sandpapers together, and there should be gaps between them. Yes, like the gaps.
We did our best to make them flat.
Yes. So I guess it could be improved, right?
I do think that the gap in this case won't change the motion so to a large amount.
Significantly.
Yes.
Okay. So I would like to talk about. It's quite unfortunate I didn't finish like the whole motion, since if we're talking about the swing part, and we should consider torque, right? And as you mentioned that the direction changes through the whole motion, and I guess that should be part of your theory, like rather just one inch, SHN.
Hands up. Okay. The opponent summarized our discussion.
So again, appreciate what the effort from the reporter, and throughout the discussion, hopefully these force analysis, like what I mentioned, for the sliding part should be force analysis, and for the swinging part should be torque analysis, should be contained in the whole presentation. And the approximation, like for the cone and the SHN motion, is not like pretty well considered. And for that, the experimental results comparing to the theoretical results, it doesn't quite. I'm not sure if it matches, since the reporter didn't show it to me, and that is also a pity. And this is my end of my conclusion.
Okay. Question for the reviewer.
Okay, so thanks for the opponent and reporter for their presentation. The first question I'm going to ask both of you is that, do you recognize the motion as a chain motion, right?
Yes.
Or opponent, what do you think? Do you think this is a HM motion?
Yes.
HM motion? Or
I totally agree with that.
you don't agree? Okay. About next question, that's so you consider the geometry of the screw as a cone, right?
Yes.
How about it?
Well, I would consider it as a cone, but it wouldn't be the head and the edge of the screw. It should be the contact point, which it should be a similar shape, where like there's a. Oh, yeah.
I got it. Okay. Next question for the reporter. That's in your experiments, you use your hand to release the screw. So, do you admit that you have given an initial torque, or?
No, I did not give an initial torque or initial velocity.
Okay. So, next question for the reporter. Do you think that the rotation axis will move, or what kind of motion will the rotation axis for the points move?
What do you mean by rotational axis?
This one.
You mean,
It's rotating like this.
yes,
So, how will it move?
this, the rotational axis will move down the plane as this group moves down.
Okay, so think in your model that so do you think the period will be defined as a constant in every experiment?
No, I don't think
You don't think
it's
so?
any constants.
So both of the angular velocity and the period will change in.
Yes, the relative
Okay.
term, yes.
So how do your opponent think?
Are you focusing on the period or the angular?
Both.
So for the opponent, we believe that the angular velocity changes, as I mentioned in the blackboard, as it swings back and forth, and if the angle between the middle is increasing, which means the angular velocity should be larger in the end of
Okay.
the end.
For next question for reporter, so do you admit that the Rex friction for this part is controlled for the constant? The friction?
Yes, I think that we make sure that every sandpaper is the
Okay,
same.
so next question, do you think the motion is a pure rolling motion? Or there be slide?
You mean X, Y, you mean sliding down?
Yeah.
We believe
Time's
that
up. Reviewer have 2 minutes to prepare. review textbook work.
Okay, honorable juries and fellow competitors, I'm the reviewer from Team Scientist, Team High School, and today I'm going to review problem 9, oscillating screw. Also, here's a summary of the report. So, the first one is the understanding of the problem, that the reporter gives us the incline and the angle of the shape of the screw and the ramp, and also the screw shape is considered. And next is that the increasing angle of the screw's oscillation motion and the increasing tangential gravitational velocity. And the theoretical analysis that the reporter do is they assume as the geometry of the screw as a cone with the diameter equal to the pi and the radius. And the second is that the reporter think the motion as a SHM system. And the third is that they have derived the equation of the period. And about the experimental confirmation, that the first reporter do is the parameters, which degree of the incline angle and the centimeter of the screw, and also the coefficient of the friction of the screw, and also the manner of or increasing sliding in the end. And here's the reporter's performance. That the merits of the reporter is that they consider many parameters, which is well considered. And the second is they have clear video and graphing experimental results. And the third one is they have convinced experiments data. And the possible next steps for the reporter could be, the first one is the lack of explanation of using a cone to assume the geometry of the screw. And the second is they have lack of explanation in graphs period. And the third is they have lack of comparison between the theory and the experimental results. And here's the summary of the opposition. The points that they have discussed is about the point out of the define of the height in the geometry of the screw. And the second is that they have discussed the friction force on the backboard, about the static friction or the connective friction, and the sliding mode and or the pure rolling mode. And the third one is the acceleration part and the deceleration of the screw's oscillation. And here's the opponent's performance, that the merits will be the point they point out the missed point by a reporter. And second is that they help us to understand the motion of the screw. And the possible next steps for the opponent is that they might be able to control the time of the summary of the report. And here's the discussion parts that the fourth direction that opponent and reporter discussed is that they drew on blackboard, and we agree with the opponent. And about reverse questions, we have asked about the SHM oscillation. The reporter think they agree with it, but the opponent did agree. And we think we can use other oscillations modes to describe it. And about next question is the cone geometry of the screw, and the reporter agreed with it, but the opponent doesn't agree with this geometry. We think as a true contact point oscillation will be considered in the further investigation. And in the next question is the initial torque that the reporter does think so, and we think that the reporter can improve by control by the machine to avoid the initial torque. And here's the general suggestion that will be just as I mentioned, that you can use the machine to control it, and maybe the friction parts will be controlled by maybe using a longer sliding ramp. Okay, thank you.
Reporter,
So this is the reporter column number 9 operating screw conservative. Okay. So in theory, we used a cone as the screw model and an SHM model as the oscillation parts of the theory. And the experiments, we use different friction coefficients and the length of the curve and different inclination angles for our different parameters to discuss. And I believe that the model and the experiments does need quantitative comparisons, but the qualitative conclusions are proven in the experimental results that we had for the theory. And also, the model of the cone and the screw does need improvements, but I do believe that the approximation of the cone to the screw is necessary for is enough for this experiments to be made. And so thanks to the reviewer and the opponent for your recommendations about more precise experiments and the qualitative analysis of the experimental results and the theoretical results to make sure that everything does match. And thank you.
Question from the jury.
So a question for reporter. You use different sandpaper with different numbers. Yeah. Do you know how the friction change with that number?
I know that the number means how many like little dots are there on the sandpaper per area. So I do know that the lower the number, the higher the friction coefficient.
How when the number increased by like 2 times, and you know how much your friction will increase or will reduce?
No, we did not calculate how the number of the sandpaper is.
So during the experiment, we recognized that the screw may go in the direction of x-axis. Yeah, not only in the y-axis. Yeah, I think the opponent proposed a very good idea that the friction depends on the angle. Yeah, so can you speak more in advance to explain this phenomenon?
Well, may I elaborate on my whole idea on that board?
Yeah.
Thank you. So, in my opinion, there are 4 phases of the screw motion. So, firstly, as the reporter just said, there should be one of the components.
Cut the question more precisely. Do you think you can calculate, or you can estimate, or you just explain it? Explain.
I think I could stimulate the whole motion by
No, I mean,
analyzing the whole.
can you explain it, or you can estimate, or you can calculate?
I can
Which stage you can do?
explain.
I think that's enough. Any question? You can go down. I'm sorry, I have to cut it because we don't have too much time.
So I will have a question for three. So do you think it's enough or it's suitable to model the screw used as a cone? Do you think is it suitable or enough to?
I would assume the whole model into a cone, but the contact point would not be the edge and the hat. Yeah, elaborate on that word again.
So we just consider, we just answer this one.
We don't think that it's suitable to use a cone geometry because I would think use a true contact point oscillation will be more related to the real model.
We believe that the cone approximation is enough for the experiments, but for further precise, more precise theoretical predictions and results, we would change our model.
Have you ever tried to use the nail instead of the screw? The nail,
No, I have never tried it.
iron nail. Do you know the iron nail?
Yes, I know. Yes. I didn't try.
Okay, question? Okay. I have a question. Actually, the reviewer has asked, but I just want to make sure. How do you measure the theta angle?
The theta R angle is here. So when the screw is yes.
Okay. Any question? The other question, that's my suggestion. Actually, you can measure the x versus time, y versus time, because I think it's oscillating,
Yes.
somehow oscillating. It will provide the discussion you have just on the background. Okay. That's it. Okay. Review. Let's keep the floor. Okay, for the reporter. Seven, 8, 7, 7. For the reviewer, for the opponent. 8, 8, 8, 8, 7. For the reviewer, 6, 7, 8, 8, 7. Okay, that's it. We have 10 minutes break. I'm going to change the recorder for the proper. 1 minute.
The opponent would like to challenge problem number 1, grab your fingers.
Honorable judges, for the opponents, this is the team we have so and we accept the challenge.
那他们的那个布，你说的。
to Louis Campbell, and today I'm going to be presenting problem number 1, fractal fingers. So in my presentation, I will first do the introduction of the problem, and next I will talk about the theory, and then the experiment as the summary. So for the introduction, fractal fingers is the effect of fractal fingering can be observed in a droplet of an ink alcohol mixture is deposited onto diluted acrylic paint. How are the geometry and dynamics of the fingers influenced by the relevant parameters? And our focus will be focusing on to investigate the relevant parameters and analyze the geometry of the fingers. So as you can see first, this is on the right side of the slide is a video of an alcohol mixture droplet, and as you can see, as we dip the droplet on the surface, it will start to diffuse, and in the end, it will break down to fingers. However, on the left side, it is the pure ink droplet. It will not diffuse, and it will not break down into fingers. And for our experiment setup, we use diluted acrylic paint, which we use pouring medium to dilute the paint. And as for the droplet, we use ink alcohol mixture, and the alcohol we use is isopropyl alcohol. And this is our experiment setup. So we use paint to control the volumes of the ink alcohol mixture to 0.01 milliliters, and we also use a stand to control the height between the tip and the surface, so we can control its initial velocity of the droplet. And another experiment setup is to uniformize the thickness of the diluted acrylic paint, which is as the base. So our solution is we will first put an adequate amount of paint on this transparent plastic film, and we'll use another piece of transparent plastic film to spread them out into every corner of the film, and we will measure it on the scale to make sure that it's on the same weight. So since that we cut the film in the same size and we measure all the paint in the same way, so we consider that we can uniformize the thickness of the paint. And so before my discussion, I want to introduce some terms of the fractal fingers. So first is the red area, the red circle, which is representing the inner circle. And as for the outer circle is the green, the blue area. And outside the outer circle area is the finger area. And the purple line is the fingers one. And that's the green circle representing the whole circle, and we'll later discuss how we will define it. So as for our data analyzing, we use ImageJ and color picker. And well, since we don't think we can really we cannot really define a finger. What is a finger in the structure? So we use color picker, so which is to investigate the difference of the gap between which is the color length. Yeah, which is to investigate the color length of every section. So we will define like maybe if the gap between the column is bigger than 60, so we'll define it as a finger. And we also use ImageJ to measure the length and the diameter. So there are two theories. I'm gonna back up this phenomenon. So the first is Marangoni effect, and I will use this to represent how well the droplet diffuse and then stop in the end. So Marangoni effect is the mass transfer along an interface between two phases due to a gradient of the surface tension. So you can see at the picture, the middle of the droplet is low surface tension, and it will expand to the area with higher surface tension. So in fractal fingers, as we dip the ink alcohol mixture on the surface, because of the thickness difference of the droplets, so we believe that on the outer side of the droplet, because it is thinner, so the alcohol will evaporate faster, so which causes the lower concentration of the alcohol, and it will also causes the higher surface tension. So it will fit the theory that we put first, that the low surface tension in the middle will reduce to the higher surface tension on the other side. And as for how it will stop, we believe that it's because all the alcohol in the droplets is evaporated, so there is no concentration difference in the droplets. So it will, and thus there's no surface tension difference. And as for the phenomenon in this case, this is Marangoni bursting, and which you can see is quite different from fractal fingers. So we believe that the difference is the Marangoni bursting, the base is the oil, while fractal fingers is the diluted acrylic paint. And the phenomenon that it will, in Marangoni, it will form thousands of tiny droplets. However, in fractal fingers, it will form fingers of the branches. And the similarity is that the droplets are both in alcohol mixture, and the theory is both about the difference in surface tension and vapor pressure. And the second theory is the viscous fingering. So I'll break down into two parts. The first part is the viscosity. So viscosity is the resistance of a flow. The higher the viscosity is, the smaller the fingers are. And we also convinced that the diffusion of the fingers is random, so it is unpredictable. And the later is the surface tension. So in this equation, we concluded different force, and as the basic algebraic manipulations, we find out that as the gamma, which representing the surface tension coefficients, increase, the A, which is the radius of the tiny droplet, will decrease. So we'll explain it this as how the fingers perform. So as for our experiments, the first parameter we change is the time interval. So time interval represents the time that we finish spreading out the white paint until the moment we dip the droplet. So because of so as you can see in the graph, as the longer the time interval is, the smaller the fingers, one's whole circle, and the inner circles are. So we believe that it's because the higher the time interval is, the more viscous will the white paint will be. So it will cause smaller fingers. So this is our experiment results under the microscope. As you can see, as the interval increase, the fingers' length will become smaller. Okay, next is the diluted acrylic paint concentration. So as you can see, as the concentration of colored medium and the diluted acrylic paint increase, the whole circle, inner circle, and the fingers one will all increase. Well, we believe that it's because it becomes because the viscosity will decrease, so which cause smaller resistance to the fingers, so it will diffuse bigger. And so this is our results. Oh, and as you can see in the picture on the right side, it's kind of bleeding. And to define how degree it's bleeding, we will use the parameters per lens to define. And as the parameter concentration increase, the parameter per lens will decrease. So next is the isopropyl alcohol concentration. As the isopropyl alcohol concentration increase, the bigger the fingers will be. Well, we believe that it's because the proportion in the alcohol and the proportion of alcohol in the droplet is, it will cost more time to evaporate all the alcohol, so which needs more time for them to diffuse. And this is our experiment results. Okay, next is the alcohol mixture volume. So it's quite an interesting part that the fingers of the length of the fingers didn't increase, but well, we believe that And however, the finger's area decreased rapidly. So we believe that it's because the difference of the diameters of the circle. So even though the finger still stays the same, however, the actual amount of the actual amount of the ink that becomes fingers will increase. So next is the isopropyl alcohol evaporation time. So as you can see in the graph, we discovered that the evaporation time didn't really affect our experiments. So next, since the problem statement didn't mention about what kind of alcohol should be used in the experiment, so we have tested different alcohol with different carbon atoms. So we found that when it has 4 carbon atoms in the mixture, it will become more oily, and it cannot mix well with the ink. And you can see that the isopropyl alcohol has the longest finger, so we choose it as our experiment ingredient. So next is the temperature. So you can see that in the degree before around 40, the fingers length stays the same. However, after 40 degrees, it will decrease and will decrease rapidly at the end. So we believe the reason why it will decrease rapidly is because all the alcohol evaporates, so there is no fingers forming. And next is the summary. So the patterns will correct your fingers form randomly, so they cannot be predicted. And this is the end of my
Okay. Questions on the opponent?
So thanks for the report. The first question I'm going to ask the reporter about is that do you think that the geometry of the outer plane that you have drawn on a plastic plane will affect the motion?
I think the thickness will affect because
The thickness?
yes.
Okay, so you use the outer diameter of your fingers as a measurement, right? So, okay, so I got your point. And next question for the reporter is that, so are we able to describe, according to your theory, that you aren't able to describe the gradient or what the gradient of a surface tension will be, right? Or maybe you can describe it with a formula. So, okay. For the next question, that so do you think the most varies from this Maragone effect, which is by the oil, as you mentioned, and the in comparison to the fractal fingers, that what do you think that would hold those droplets together in fractal fingers, not separate?
Well, I think the difference between them is because oil is a non-porous medium, while acrylic paint is porous medium. So I think there will be force for the inks to stick in the form.
Okay, so next question. So you would in your formula about surface tension, so you think that's the radius of the outer diameter of the
Time's up. The opponent prepared to report.
affects the flow. Honorable juries and fellow competitors, I'm the opponent from King Scientist Junior High School, and today I'm going to oppose problem number 1, fractal fingers. And here's the problem statement. The problem statement may focusing on the fractal fingering and also the ink alcohol mixture, which is the ratio between it, and also it will lead to the geometry discussion of the fractal fingers. So we focus on relevant parameters investigation and geometry of the fingers. And here's the structure of the reporter's report. That first it starts with observation video with pure ink droplets and ink alcohol's observation, and the theoretical model about the Marconi effect and the surface tension, which is discussing about the surface tension effect and the setup about the dialectic algorithm paint and ink alcohol, and they use uniform size of thickness. And the experimentation that they measure the length and the diameter of the drop of the fractal fingers, and they use time interval to describe the experiments, and they do concentration, and their conclusion is that. And about the strong points and weak points of this reporter is that they have clear definition in terms and different terms of the droplets, and they have good experimental setup, and they have clear explanation of the Marconi effect. And of course, as they compare Marconi effect and the fractal fingers together. And the fifth point is they compare various alcohol between each other and show the geometry of them. And about the weak points of the reporter is that the first one, they are lack of explanation in the experimental error, and they have lack explanation in the temperature's effect. And the third one is they have no conclusion between the experiment and the theory. And here are some points that I will discuss in the later discussion. Then first, I will start with the observation about the rings geometry and also the experimental setup, which is the geometry of the acrylic paint. And about the theory, I will discuss about the explanation of Marconi effect and also describe of the surface tension. And maybe I'll discuss something about the viscosity difference, since the reporter has said in her reports. And about the experimentation parts, and I will focus on the boundary conditions discussion and also the graphs discussion. Okay, so next move to the next one. Okay, so the first question that I'm going to ask the reporter about is, why do you think in your observation parts, why do you think there will be a white ring? Geometry, the white ring. What do you think is the main cause of the white ring's geometry?
Well, I think it's the Marconi effect.
Yeah, but Marconi effect describes the surface tension gradient, which the flow will flow from the low surface tension to high surface tension. But it seems that in the inner space, that the flow is more slow and the outer space is more faster. So they have their higher surface tension in the outer place. But why would that happen?
Well, it's because the concentration difference between the inner part of the droplet and the outer side of the droplet, which the outer side of the droplet has lower alcohol concentration.
Okay, I understand your point. So let's move on to the next discussion about in the geometry of the arcade paint. Could you please move on to your yes. So do you think you said that you come to the same thickness?
Yes.
So what do you think if the thickness is not the same? Because you cannot prove it's the same thickness. So imagine what the different thickness will cause the phenomenon.
If the thickness is not even, because I think the thickness will affect the degree of the degree that the acrylic paint will dry, and which which cause the different viscosity. So if it is thinner, the friction is thinner, I think the fingers will be shorter.
So if thinner, so the viscosity difference, the fingers will be more shorter. So in this part, the opponent agrees with the reporter, and so since this problem is discussed, then let's move on to the next problem about, please turn to the page 21. So about this showcase that why do you think some of them grow bigger, and there are some variations in the middle of two identical figures.
This part.
Yeah.
Well, I think we can separate into two sections. I think the fingers will first grow with the main branches, and then it will grow the branches outside here. And I think it's because the difference of velocity as the resistance the base gives the outlet, because the decrease of the velocity, so it will grow like shorter.
It's caused by viscosity.
Yes.
Okay. So next, please move on to page 25, which I'm going to ask the reporter about why will this line be so strict?
Well,
Please.
well, it's our experiment results, and yeah, so yeah, this is what we have. This is what we have seen in our experiment, but we think it is acceptable because I think the main focus we're focusing is the fingers area, like is the fingers area, which is the blue line.
So this is the area. It's not focusing on the
Yes,
surface.
exactly.
Okay. Okay, so next move on to page 27, which I would like to ask the reporter to explain to me why there's a lack of fingers in different kinds of alcohols, since these alcohols have varied and have a specific like geometry.
Sure. So, for the butanol alcohol and ethanol, I think it's because they cannot mix together with the alcohol. So yeah, and I think it's the properties of the alcohol, which is because, as you know, this is alcohol has the hydroxyl group in the end of the molecule, and it can connect with the water with hydrogen bonds. So as the numbers of carbon atoms increase, the less properties of the hydroxyl group will.
It's about the properties of
The
alcohol. So okay, I got your point. And let's move on to the next question. Do you have a graph comparison between the concentration and velocity of your?
Oh yeah, we did. You mean the velocity, you mean how the
Velocity.
how the droplet expands? Yes, we have tested that, but in our results, we cannot find find a trend in it, so we just
Okay, so another question about the recorder is that, so since your theory only explains the numerical effect, that's right?
and also the viscosity.
Viscosity. So can you describe how the viscosity difference between two fluid will affect the speed and also the geometry of it?
Because viscosity gives the, I think the viscosity in the base will give the resistance to the droplet. Yeah, so as the viscosity increases, sure about the figures.
So,
Which it will stop expanding earlier than the base with higher viscosity, with lower viscosity.
which parameter do you think affects the most on this phenomenon, the viscosity or the surface gradient, surface tension?
Well, I think there are two parts. The first part is the concentration of the acrylic paint, which I present beforehand. And the other part is the thickness of the white paint, but we have already controlled as so we didn't test it.
Okay, so about next question for Jordan, that so if you change the surface tension gradient in the higher level, that and the viscosity also is fixed, then so the let's skip the question. Oh, okay. So next question I'm going to ask about is the alcohol's thickness. Do you consider the shape, the geometry of the droplets in your experiments, like beside you?
As what I mentioned before, we have controlled the volume of the droplet, and we also control the height between the tip and the surface. So I think we can control the shape.
So you control the shape, then well, since your radius is bigger, that the thickness will be smaller, right? The thickness of your alcohol mixture. So in this part, that your ink alcohol mixture, do you think that the geometry, like the thickness, will affect the motion?
You mean the droplets?
Yeah, the droplet thickness.
Time's up. The opponent summarized.
Okay.
Sorry, mistake. Go ahead.
Well, I think it will cause difference in the evaporation time of the evaporation speed, as I mentioned before. Yeah. So I think,
Yeah. And next question is that, so you think which affects the phenomenon the most, the evaporation rate or surface tension or viscosity in the geometry of your rectangles? Next
well, I
one.
think, I think as for the fingers, I mean the fingers part it's about surface tension and viscosity, but as the whole phenomenon for diffusion, I think it's very many effects.
Okay, thank you. And next question is that, do you think there will be a boundary condition of the length of the radius? That's what will stop. Will it?
Yeah.
Still?
Time's up. The opponent summarized.
In my observation that I have discussed the main points about the parameters in the experiment, which about the Margot effect, which is surface tension gradients, and also the effect of the evaporate and also the viscosity difference. And in other discuss that we have discussed about something like the geometry of the thickness of the ink alcohol droplets, and we also discussed about the boundary condition that the reporter thinks the droplets fingers will have stopped in a kind of radius. and you can also agree with the reporter. And I think that is all of our discussion, and thank you.
The reviewer takes the floor to ask the question.
Okay, I have some, I would like to know first, the reporter. So can you tell what is the main parameters that affect the fingers? What's the main parameter?
Well, I think it's the concentration.
Okay, opponent?
Yeah, I agree with the reporter, which is concentration of the experiment.
Okay, then I would like to know how do you define the finger?
We cannot define the fingers as you can see. As you can see in
Okay, so and opponent?
I think the recto can be defined as a algorithm, but in this experiment that is kind of random. The randomness is big, and we cannot give it a clear definition.
Okay, then
oh well, as you can see, yeah, you don't know whether I can define this as a finger. So yeah.
okay, then I would like to ask, reviewer first, what is the reason why the finger forms?
The fingers, oh yeah, so I think it's the surface, I think it's the surface tension, which I have mentioned before. So as the radius of the droplets decreases as it extends. Yeah.
Okay, so can you tell me the difference between the here and here, the surface tension here and here? Can you tell the difference? Because here they may form the finger like that, but here it.
Well, I think it did like see the pictures on the right that imagine yes that there is small fingers from between two large fingers. So I think every area will form little fingers, but because like the limitation of the space, so it will cause smaller.
Okay. And I would like to add a comment point. So what do you think the driving force of diffusion?
The driving force of this droplet, I think, will be mainly caused by the surface tension gradient, which is the Marangoni effect. But the viscosity difference will also determine the velocity of it.
Okay, then reporter.
Well, I think it's a concentration.
Okay, so like there's a circle that you call D1. So what is the turbulence between extended length and viscosity? Reporter.
In phase one. I think that is about.
Okay, then. Oh, sorry, then.
Time's up. Preparation for the reviewer. reviewer, take the floor.
Okay, then I'm the reviewer of Typt, and my name is Chen Shizhen. Okay, so this is the problem here. So here's pros and cons. The reporter will explanation of phenomenon with video and precise experimental data, clear image for each experimental result and explain every graph. But cons is no quantitative comparison between the parameters and lack of the theoretical explanation associated with a two experiment. Lacking of definition of the parameter and figures and incomplete explaining by using random. Okay, opponent. And the process having to focus on the mistake the reporter had and focus on experimental results and focus on how experimental results can be explained quantitatively. The concept didn't focus on the theory and ask questions but didn't try to discuss further and missed some parameters such as temperature and drop time. So here's key question. So first opponent asked, does thickness affect and reporter's answers yes and in our view is yes. And opponent is unable to describe surface tension gradient, so reporter's answer is theory and equation. And our view is yes, the reporter failed to describe. And what holds fractal fingers together? And reporter's answer is complete can hold droplets together. And we agree with reporter. And what would thickness affect? So reporter's answer is shoulder fingers when there is thicker paint. And our view is same with reporter. Now opponent has two straight of graph data 25 and reporter's answer is our result. And in our point of view, reporter should explain more results with the theory provided. Then what types of alcohol make a difference? And reporter's answer is properties of alcohol. And in our point of view, reporter should have an explanation for why it's isopropanol and butanol have some difference. Then what is the main parameter? Reporter's answer is concentration and distance. In our point of view, diffusion rate is also important. Okay, so opponent asks, does friction affect motion? And reporter's answer is the friction will cause difference in evaporation speed. And in our point of view, friction is not as necessary in this case. So is there a boundary condition? Reporter's answer is yes. And in our point of view, yes, but not unpredictable. So here now is reverse question. So my first question is about parameters, and opponent's answer is same as a reporter's answer is concentration thickness, and opponent's answer is same as reporter. And my question is how to define a finger, and reporter's answer is undefinable, and opponent's answer is can be defined as a problem, but it's random. And my question is the reason why fingers form, and reporter's answer is surface tension. And my another question is driving force of diffusion. Reporter's answer is concentration, and opponent's answer is surface tension gradient and viscosity. And my question is relevance between expanding length and viscosity, and reporter's answer is no relevance. Okay. Then that's all of my report. Thank you.
The final result from the report.
I will do this and we're going to this my concluding remarks. So first, for sure I should have managed this one better. And second, as what the reviewer mentioned about the alcohol difference, I think maybe I can explain one more time. So it's because what caused the solubility of the alcohol is the hydrogen group of the molecule, and as the number of carbon atoms increase, that part that the hydroxyl group part, the density of that part will decrease. So that causes the property difference. And I don't think the opponent did mention friction in the discussion, but the reviewer said it in the presentation. And yeah, and I should elaborate more on the boundary condition of the possibilities. And this is the end of my concluding remarks. Thank you.
Okay. Question from the jury.
So I have a question for three of you. First for the reporter, you explain your phenomena using surface tension and the viscosity and the evaporation. It's all physical speed because you have tried different additives.
Yes.
Do you think some chemical reaction could happen in your experiment?
Yes, I do. So,
Do you think so?
yes, I do.
How do you know? Maybe for opponent, do you think there could be some chemical reaction in the experiment?
That there may be some chemical happens in the experiment, but we are not sure about how it happens.
So in my opinion, I don't sure if this is really a like chemical reaction, but it's like the moisture in the paints will mix with the alcohol and change the viscosity.
I have a question for you three. So the question of this one is how are the geometries and the dynamics of the fingers? So do you think how to characterize the dynamics in this problem? Because the question want you to discuss the dynamics of the finger. So, but I think you don't consider the dynamics. So do you know how to characterize the dynamics of in this problem?
Well, I think I can investigate the expanding speed that the droplet expands, but yeah, I do mention that it's not even, so we didn't put it on it.
Dispense speed?
Yes, like when will, as we did the droplet, when will the fingers started to form? Yeah, we have tested that, and also, yeah, but that isn't.
Well, Newton thinks that maybe we can start from the driving force caused by the surface tension, and then these two, the geometry, which is the thickness of the droplets, and it will also cause some deviation during the process. And we can lead to a physical model with by adding the viscosity difference inside of it. So we can describe the dynamic of the vertical fingers. Thank you.
I agree with opponent's point of view, and in my opinion, I think there's one more term, just like the droplets just drop and the liquid just go out, and the force that caused by the like pressure, the difference between the center and the end point pressure, so it pushed the fingers forward. It stops until the like resistance force at the surface and the force that is caused by the.
Okay, that's it.
Yeah. So for the reporter, for the experiment and the theory, what is the role for you on this investigation? Is there any other people also joining on this project?
Yeah, we did the experiment together.
Okay. Yeah.
Okay, that's it. So let's go to for the reporter. Seven, 8. For the reviewer, for the opponent, 6, 7, 7. For the reviewer, 6, 7, 6. Okay. That's the final of today's tournament. Okay, this section.